up to now, I have introduced notation so that we can write down a differential, and the homology, I told you, is a vertex algebra again. So I have given a construction of a zoo of new vertex algebras called W algebras, and they are and now the additional thing is they are associated to nilpotent elements. Okay, and now.
Excuse me.
Yeah.
Just a quick question. Just now you told me that the cohomology of the complex vanishes except at degree 0. How do we know that?
Yeah, that's one of the main theorems.
Uh-huh.
Now we want to establish structural properties. And so what does one do first? One simply tries to compute a few fields in cohomology, or in homology, and see what kind of fields there are. And so properties, the first property is you can find a Virasoro field. Do you want to see the explicit formula? Yeah? So there is a field, let's call it L for Virasoro, and it's a linear combination of 4 terms. It involves the original Virasoro field of the affine vertex algebra, the derivative of the field associated to X, and then 2 more called the Virasoro field of the chiral fermions and of the neutral fermions. And and L Sugawara is the Sugawara vector that I had at some point. It's the field associated to the Casimir element of the Lie algebra. So here we go over a basis. If I take a lower index, I mean the field corresponding to a dual basis vector. I will not introduce the notation for that now. And then L chiral and L neutral are Virasoro fields for the free field algebras. And here, where this number m alpha is equal to n if the corresponding basis vector has eigenvalue n. And the neutral part is given by the I will only say in words what this upper index means. It means the same thing I do here. I choose a dual basis, and then it's the fields corresponding to the dual basis. Okay, and now the statement is that L is a Virasoro field of the homology, so it's non-trivial in the homology, and the central charge let's call it the central charge, depending on these 3 parameters. And it's the central charge of the affine vertex algebra, which is given by the superdimension of the Lie algebra, times the level, divided by the shifted level. Then this derivative of x gives a correction depending on the norm of x. Then we get a term coming from the phi alpha free fields. And then finally, the dimension 1/2 fields give an extra contribution that just depends on the super dimension of G1/2, difference of even and odd part. Okay, so this W algebra always has a Virasoro field. That's the first question you want to ask. And the way you check it is by, well, you verify that it's non-trivial in cohomology in particular. Well, it's a computation. By the way, all these the results I'm presenting here are established roughly 20 years ago, so not that long ago, by Rowan, Victor Katz, and Wakimoto. Okay, and the second.
What is that? What is BDZ What is X?
X is the field corresponding to X, the X of SL2. That gave us the 1/2 integer grading, the element of the Cartan subalgebra of SL2. Right? And remember, I introduced X because the convention here is that one has half integer grading, and the X is the 1/2 the standard H of SL2. Okay, the second property is that one first introduces fields I alpha, so they are our original fields of the affine vertex algebra, and now corrected by a lengthy expression. So here you have a certain bilinear in the fermions, and you have another certain bilinear in the other type of fermions, free fields. And here again, this upper index means it's the field phi corresponding to a vector dual to the vector q beta. Dual with respect to the bilinear form that we use. And further, we introduce the subalgebra A to be so we have F as a nilpotent element, so we have a subalgebra that is annihilated by F. That's this G upper F. So it means this is really the space of lowest weight vectors with respect to this SL2 action. And it might happen that they appear actually trivial representations of SL2. And this A is really the Lie subalgebra of G of trivial representations of SL2 with respect to this SL2 action. Now, and the next structural property is that this I alpha for Q alpha in A give also non-trivial states in the W algebra. So for Q alpha in the subalgebra A, the I alpha are elements of our W algebra, and they generate an affine vertex algebra of type A, And there's an explicit formula for the level, but it's long, so I will not write it down. Of some level, of some explicitly known level. And it depends on various bilinear forms that we have here. I don't think that it will buy us much here to tell you exactly this. Okay, so these are the first two. Right? We have this W algebra, and we want to know what type of fields does it have. And now And these are the two basic things one can immediately verify. We have a Virasoro field. It has a certain explicit central charge, depending on the data that we know. And it has an affine subalgebra if and only if the SL2 action that defines this W algebra has a trivial representation. Trivial representations appear the Lie algebra G is an SL2 module, and the trivial module appears in there. So let's maybe also give an example. So, or let me just draw a big matrix. Right? We can take a big matrix. Now we can choose a nilpotent element. One choice would be just to draw a big upper block. So you should think about it. This is SLN plus M or GLN plus M. And then I choose the GLN subalgebra. I do my principal embedding in here. So then what happens is it means this upper block will decompose into a bunch of irreducible SL2 modules via this embedding, none of them the trivial one. Here we will get a bunch of n-dimensional representations, here the same thing, but the whole big block here will give us an GLM of trivial representations. So in this example, for this type of nilpotent element, which we would call the nilpotent element of type Fn, M. So here, we would have that this A would be GLM. Right? And then the statement would be that in that case, the W algebra has an affine Lie algebra of type GLM as subalgebra. So now one has to ask what kind of additional fields does it have, and now the statement is that let me say it in words, and then I will write it down and explain these words more. The main theorem is that so first of all the associated graded of the W algebra is the affine vertex algebra of GF, of the Lie algebra of lowest weight vectors of SL2 in G. In particular, to every element, to every lowest weight vector with respect to this SL2 action, I can identify a field of the W algebra. And then one can be more precise, and one, in fact, the W algebra is what one calls strongly and freely generated by these fields. So that's the main structural theorem, well, it's a spectral sequence argument that is in fact not that long to verify this, but yeah, let me write down this statement and tell you then also what strongly and freely generated means. So, for each basis vector that is an element of, that is also a lowest weight vector of F, and of course the SL2 weight of a lowest weight vector needs to be non-negative, non-positive. It needs to be.
Can you say once more what is GF?
The Lie subalgebra of G that is annihilated by F, the space of lowest weight vectors of G as an SL2 module via the embedding that defines our reduction. So for each such basis vector, there exists a D0 closed field K alpha, whose conformal weight is determined by the SL2 weight of conformal weight n plus 1. Right, so this, at the moment, in the previous statement, I told you what happens for n is equal to 0, because that's, and in that case, we get an affine vertex algebra that is generated by these currents, these x of z that I have always written down. They have conformal weight 1, 0 plus 1. And now it turns out more generally, if I have an SL2 representation appearing here, whose lowest weight is minus 3, then the conformal weight of the corresponding generator is 4. And, okay. And the homology classes of these fields, K alpha, where the corresponding Q alpha give us a basis of the space of lowest weight vectors of G. So these fields strongly and freely generate the W algebra. And that is a very good information. So let me tell you what these two words means. So in the affine case, I have we have this what I had called a PBW basis. We had a basis of ordered monomials, and each ordered monomial was nothing but a word in the negative modes. So this means every basis vector is just it's just such a monomial. But what is the mode x minus 1? That is the x minus. I mean the vector x minus 1 on the vacuum corresponds exactly to this generating field x of z. What about x minus 2 acting on the vacuum? It corresponds to the derivative of this field. X minus 3 corresponds to the second derivative, etc. So every mode itself is the you have corresponds to a derivative of a generating field, and in that sense, strongly generating means. So strongly generating means that every field you can write as a normally ordered polynomial of your generating fields together with their derivatives. In the affine vertex algebra, we have seen this. On the level of the underlying vector space, this is a statement that every vector of the underlying vector space you can write as a linear combination of monomials in the negative modes of the strong generating fields. So this means it's this whole thing, this strongly generating, is a statement about the whole structure of the vertex algebra. I'll write it down now. So in this sense of this sentence, the strong generators are the important information you need to know about your vertex algebra. It means you hopefully find a finite set of fields. For example, for the affine vertex algebra, this finite set of fields was given by the fields associated to a basis of your underlying finite dimensional Lie algebra. And then every field can be written as a normally ordered polynomial in these fields and their iterated derivatives. And so that in particular, the modes of any fields can be written as infinite sums of polynomials of the modes of the fields of the strong generators. And so then what it also then means that the underlying vector space has a monomial spanning set given by monomials in the negative modes of the strong generators. So this strongly generated is a good structural property. So in particular for the W algebra in question, in order to understand this basic structural property, what you do is you take your big Lie algebra, you choose your SL2 embedding, you decompose your big Lie algebra into SL2 modules, and for each irreducible component, you read off the lowest weight, and you take this theorem and says, okay, I have a lowest weight for example, lowest weight minus n, then I get a corresponding strong generator of conformal weight 4. And so that means I at least know via the structural theorem what type of vertex algebra in terms of strong generators I do get.
Excuse me. Could you explain what do you mean by normally ordered polynomial?
I have introduced this normally ordered product, right? And you can iterate this. So what you can do is you take a monomial in fields, right? So for example, you have your 7 fields. You take the first one times the second one times the fourth one, maybe squared or so. And but you know the product of fields at the same insertion point. We discussed this doesn't make sense, so we have to take the normally ordered product. So we take the normally ordered product of first, second, and fourth. And now I want to be a little bit more general. I also allow for iterated derivatives. For example, I could mean the fourth derivative of the first field times the second derivative of the second field, and so on. Okay.
It was some result from before that this normally ordered thing is a well-defined endomorphism.
Yeah, exactly. That's what we discussed before. It's well-defined, and I use here a short hand notation. I mean this iterated normal ordering nested from the right. So you'd first take the 2 rightmost term, then normally ordered product. Then from that on, answer is well-defined. I take this normally ordered product, the normally ordered product with the 3rd rightmost one, etc. Okay.
And you said that this is equivalent to just as a vector space being generated in negative mode of these guys.
Yeah, exactly. And freely generated then means that these negative modes, these monomials form a basis. And so if there are no normally ordered relations, and it could of course be that a certain normally ordered polynomial of strong generators and their derivatives simply acts as 0. And freely generated means this will never happen. There are no relations between normally ordered products. Okay, and
Vertex algebras we've seen so far are also strongly and freely generated by someone.
yeah, exactly. So the affine vertex algebra was strongly and freely generated by the fields associated to a basis of the Lie algebra. The free field algebras were strongly and freely generated by the fields associated to a basis of the underlying vector spaces. In general, the theme is these universal vertex algebras where we don't quotient by anything have a good chance to be strongly and freely generated, but homomorphic images of those will almost never have that property. So in particular, interesting vertex algebras, from the representation theory point of view, won't have this property. Okay, the final statement is that this homology is somehow naturally graded. I'll say in a moment how. And the complete homology is graded in a single degree. Where we get an integer grading on this complex by assigning the phi alpha degree 1, the phi alpha with alpha lowered index degree -1, and all others degree 0. And, okay. Any questions?
Excuse me, I didn't understand the last bit. Why don't you talk about degree of phi alpha?
Here I've introduced just a differential and a vertex algebra on which it acts, this big C, and now you make it into an integer graded complex by this assignment. Via this assignment, this D0 has charge 1, and so that then it is a Z-graded complex, and it turns out the homology is completely concentrated in degree 0. I'm just writing this down for completeness because conceptually this is an important, useful thing. And maybe let me comment on the proof. What you have is you have this big complex. What you do is you split it into split it into a subalgebra generated by this phi lower alpha together with their images under the differential. That you check that this is a subalgebra. It's a subalgebra whose homology is obvious trivial, and then you find another subalgebra to which, for example, this phi upper alpha correspond to, and you observe that other subalgebra is also invariant under D0, so that the homology of the big complex is the homology of the tensor product of the homologies. Well, one of them is trivial, so you reduce the problem to the homology of a much smaller vertex algebra. That much smaller vertex algebra is semi-infinite, is only graded by either non-negative or non-positive integers, depending on how I defined it. And on that one, the differential is quite nice, so that you can compute the homology fairly quickly, so that you get this structural theorem. So it's important for structural purposes, but we will not use it further. Okay, now, yeah?
If VOA is not strongly generated, then how can we present general field? How to present if not strongly generated?
Every VOA is strongly generated by the complete collection of its fields. Every vertex algebra is strongly generated by the complete collection of its fields. All right? So the non-trivial statement is strongly generated by a set of fields. So this means The non-trivial statement about this one here is that this set here is very small, right? So it is a minimal strong generating set, and that is in particular reflected in this freely, right? So of course I could have added, for example, the derivative of the Virasoro field as an additional strong generator. Still, the VOA would of course be strongly generated, but I would have a normally ordered relation, namely the strong generator L, its derivative is equal to its derivative, so I would have a relation. And it would tell me I would have added one strong generator too much. Right. But one question you could ask, right? Every VOA is strongly generated by its complete collection of fields, and clearly this is total overkill. This is way too much, right? So you can ask, can I find a minimal strong generating set? Or you can, in fact, better, you can ask, can you find a minimal finite strong generating set? Right? Infinite. You should think about a strong generating set as a VOA analog of a generating system, right? And we want things to be finitely generated. So it turns out for most standard vertex algebras you can do these things, but there are new modern things like this W infinity which are very important, and those are not finitely strongly generated, so that makes them substantially more complicated. Yeah, which... Okay, where am I? So we call a nilpotent element F principal. If it has the property that the dimension of the space of lowest weight vectors with respect to this SL2 embedding is equal to the rank of the Lie algebra. And if F is principal nilpotent, then one gets the W algebra of G, and one often omits the F in this case, just because these are the W algebras that appear most often. So if you look at the literature and you find something like this, then people have omitted the principal nilpotent element just because it's the most common one and historically mostly studied. Okay, and now one can play a game, so let's just do a little bit of counting. So SL2, well, what can we do as embeddings of SL2 and SL2? If you want to have a non-trivial embedding, it's just the identification. So in that case, SL2 has one SL2 lowest weight vector, that's the F, right? We look at the conformal weight formula. This F has SL2 weight minus 1, so 1 plus 1 is 2, so that means the W algebra of SL2 is strongly and freely generated by a single field of conformal weight 2, and that's the Virasoro field. Now let's take SL3. How many different nilpotent elements do we have? Well, we think about it in terms of partitions. So first of all, we can do the principal embedding. That's kind of the biggest embedding. And so now what will happen there? Well, you have to compute it carefully. We of course always get a three-dimensional representation via the embedding. SL3 has dimension 8. 8 minus 3 is 5, so whatever is remaining will be a 5-dimensional representation, and via the principal embedding it turns out to be an irreducible one. So the principal embedding of SL2 and SL3 decomposes SL3 into the 3- and 5-dimensional representation. What's the lowest weight of the 5-dimensional representation? Remember, I rescaled the h by 1/2, so it is not a -1 but -2, and so that means the corresponding field will be a field of conformal weight SL3. And so the principal W algebra of SL3 will be a W algebra, a vertex algebra that is generated by two fields, one of conformal weight 2 and one of conformal weight 3. This vertex algebra is called usually Samolodchikov's W3 algebra, because Samolodchikov in the 80s wrote this one down, and W3 indicates it's a vertex algebra of type 2 and 3. One generator in the weight 2, one in weight 3. Okay, let's maybe first go on with SL4. If you do the principal embedding there, what it turns out, SL4 is 15-dimensional. We get the joint representation 3-dimensional one, and then we have a 12 left, and it turns out the 12 is a 5 plus 7. And now we already know for 5-dimensional representation, lowest weight is -2, so we get a field of conformal weight 3. 7-dimensional is lowest weight -3, so we get a field of conformal weight 4. So this.
Could you maybe just write down those numbers for SL3?
Yeah, now I will write down. Yeah, now I write it down for SLN maybe. An F principle, and we take SLN, and then it turns out SLN decomposes into, let me call it row 3, so I denote the representations by their dimension, okay, plus the 5-dimensional, plus the 7-dimensional, and so on, and then we end up with the 2n plus 1, 2n minus 1 dimensional representation. And now the conformal weight of the corresponding generator for this one is the 2, it's the Virasoro field. This will give one of conformal weight 3, this one of conformal weight 4, this one of conformal weight 5, etc., up to one of conformal weight n. And so this means these principal W algebras of SLN.
How many? Can you just write down the numbers? It goes too fast. My buffer is full.
Yes.
I'm sure I can check this, but it would be so helpful to just write.
Yeah, and so it follows. You get a W algebra, and let me write it of type 2, 3, 4, and so on up to n. So it will be an algebra that has n minus 1 fields, one of each conformal weight starting at 2 up to n. These are called also the Wn algebras for this reason, and they are definitely the most important one. Right? You can play the game with other Lie algebras. So, for example, if you do the same thing for type B in principle, you will get vertex algebras of type 2, 4, 6, 8, etc. So you omit the odd integers, and it's then often called an even spin algebra because it only has fields of even conformal weight. And now you can do other games. So, for example, we had SL3, and the principal embedding is not the only one because we can write 3 as 2 plus 1. We can do an embedding of SL2 just in the upper 2 by 2 block. Then we immediately see, under this embedding, SL3 decomposes into a joint, 3-dimensional, plus standard plus trivial. Right? And so what that tells us that in that case, the W algebra, 3-dimensional, gives us a field of conformal weight 2, always the Virasoro field. The standard representation is 2-dimensional. It's the lowest weight vector has SL2 weight minus 1/2. So we get here a field of conformal weight 3 over 2. This is something we haven't seen before, or almost not before. So here we get a vertex algebra that is not Z-graded, but just half-integer graded. And then this algebra also has appeared a lot. It's called the Beshatsky-Polyakov algebra. It gives you another example, and so you can then go on and get many examples.
Can you just write this last statement down? So what is this example with 1/2? It just goes too far. I mean, I cannot address this if you don't write something.
I'm just giving a few examples. to give you a feeling of what type of algebras you get. So what you can do is now we think of SL3, of course, in terms of 3 by 3 matrices, and now we want to have our SL2 embedded here in the 2 by 2 upper block. So what it means is we identify our F is mapped under the embedding to the matrix that has zeros everywhere except a 1 here, right? And then of course the E will get mapped to this matrix that has the 1 here and the X to this diagonal here. And under this embedding, SL3, how does it decompose? We get, of course, the adjoint representation. But then here, what do we have here? This is just the standard representation of SL2. This here is the conjugate of the standard representation, which is, of course, the same thing of SL2. So then we get 2 copies of the 2-dimensional representation. And if we think about it, we also have 1 more on the diagonal. So we get 1 trivial representation. So what it tells us is we get here an affine vertex algebra corresponding to this trivial representation. That gives us a Heisenberg subalgebra. Each of this one will give us an even field. So the physicist would call wrong statistic field, a field of conformal weight 3/2. And then we have a Virasoro field. The corresponding W algebra is called BP, or Bershadsky-Polyakov algebra. And after the physicists who have studied it first. And why is it important? Because it's the first example you can write down of a W algebra that is not of principal type. That's the single reason. It's the first.
So it looks to me like I get 2 and then 1, 1 and then 0. I don't see 1/2. So where's the 1/2?
The lowest weight of the 3-dimensional representation is -1, of the 2-dimensional is -1/2, and of the trivial representation is 0. This is the 1/2 here. I remember the grading is given by X, which is 1/2 our usual element of the Cartan subalgebra. If you take the usual element, you would have an integer graded. It is just the convention that one takes this one. So that's where the 1/2 comes from.
How did we get from the -1 to the 2 for row 3?
Yeah. If Q alpha is in G minus NF, then the conformal weight is N plus 1, minus 1, 1 plus 1. Minus 1/2, 1/2 plus 1. Okay. When am I supposed to stop? I lost. About now, right? It's anyway a good point. So let's maybe decide. So let's just do very quick discussion. So in the next lecture, I will start with a definition of the coset, and then I'll state the main theorems, how W algebras are related to cosets, and then and then I have prepared proof ideas, which of course I can drop. I can present an enormous zoo of coset realizations. Do you want to see those? Yeah, and then I have prepared quite a bit on. Then I want to more talk and not go into big details about applications to physics, geometry, and to topology. Okay, but I will not be very detailed there, so don't expect that. Does that sound good? Good. Yeah, then let's have a break.